This is an introduction to hypothesis testing, and this is probably my favorite thing to teach in Math 1500. It's at first going to feel like you're trying to swallow a 500-pound marshmallow in one bite. There's going to be a lot of stuff going on. What I try to do is break it down into 5 easy steps. And I think if you'll just bear with me and watch the videos in entirety, that you'll find out that this is some of the easier stuff that we do the entire semester because of the way I teach it. If you try to read the book, if you try to just bypass the videos and go directly to Hawk, you're going to lose your mind. You're going to absolutely lose your mind because it's hard stuff to learn on your own, but it's not as hard to learn when you're learning it through illustrative examples. And that's what I'm going to do here, is just use as illustration how we do hypothesis testing. Now, most of you from other classes, if you are to define a hypothesis, I tend to define this as an educated guess. It's not a random guess. It's an educated guess. It's not like, what's the average wait time at Tim Hortons drive-through? Just put a bunch of numbers in a pile and just pick something out. That'd be a random guess. This is an educated guess. This is driving by Tim Hortons, going to Tim Hortons. By the way, I don't have any business stock in Tim Hortons, so I'm not. There's nothing here in these videos that I'm getting any kickback or anything. But I go to Tim Hortons. I like their coffee. I like their bagels. So in the morning, so when I'm on campus, I like to go. But anyway, sometimes I wonder, how long do people have to wait on average to get their food? And I really don't care about how long people have to wait at, 7, 8 o'clock at night, but I kind of wonder in the morning, okay? So I would probably make an educated guess. Going to Tim Hortons, when I'm in Portsmouth, I would say that the mean wait time here is 3 minutes, and I'm going to go from 8 a.m. to 10 a.m. So I'm just looking at a specific time frame here. My educated guess is the average wait time at Tim Hortons is 3 minutes, with the specific times of 8 a.m. to 10 a.m. 7 days a week. Now, someone comes in and they hear me make that claim, and they're like, you know what? I think that you're about right. I think 3 minutes is reasonable. I don't really see any reason to test your educated guess, test your claim. I think that's fine. Well, no need for hypothesis testing. If there's a claim on record, if there's an educated guess on record, and you agree with that, and you don't see any reason to dispute it, then you really don't have a fundamental reason to carry out a test of hypothesis. A hypothesis test is when you wish to test a claim. And I'll give you a 5-step procedure by which we actually test a claim, okay? Now, the first thing in testing a claim and carrying out this test of hypothesis, the very first step, the most important step in many ways, because it sets the foundation for everything else that we do. State officially what you want to test. Okay? Sounds easy, right? Officially. I want to test that the mean wait time at Tim Hortons from 8 a.m. to 10 a.m. is 3 minutes. Well, to do this, we create what's called a null and alternative hypothesis. Technically, these are hypotheses, but each of these are called a hypothesis. The null hypothesis has a notation H sub O, and the alternative hypothesis has a notation H sub A. The H sub O is a mathematical statement, so to speak. So we write H sub O with a colon. And there are three parts to H sub O. The first part is the parameter. And for you guys, this is either going to be mu or p. And over here is the value that you're actually testing. So guys, in our problem, our null hypothesis would be H sub O. We are testing a mean, not a percentage. If we were testing that the percentage of people who go to Tim Hortons has a high school degree or higher, then that would be a different type of problem. We're testing an average. And for some crazy reason, we've decided to test 3. I just threw that out there. Okay? The second part of officially testing, and this is the hardest part, is the H sub A. But we've set it up the same way. The H sub A is still your parameter. And again, that's either mu or p. It's still your value. In this case, it's 3. But we make a contradicting mathematical statement. Let's say that we have a lot of faith in Tim Hortons and we think that the wait time is less than the hypothesized value of 3 minutes. Then we would want to test less than. Let's say that we haven't had much luck with Tim Hortons. We think the wait time is longer, so we would test greater than. Many times in hypothesis testing, we don't give a direction. We just want to conduct a test just to test the claim. We're not saying we're testing it because we think it's higher. We're not saying we test it because we think it's lower. We are just testing it. So guys, when you set up your hypothesis, your alternative hypothesis, you choose one of these. Okay? So let's say that our goal here is we wish to test the claim of 3 minutes because we feel it takes longer. To get an order, through Tim Hortons from the time 8 a.m. to 10 a.m. So guys, in that situation, our null hypothesis, it's going to state the claim. Our alternative hypothesis, we think it takes longer, so we want to test that. So this would be our null and alternative hypothesis. Now, your textbook states this differently than me, and I don't like the way they do it, but it's completely and totally reasonable what they do here. They will set up the null hypothesis as less than or equal to. So in the end, we're going to make a decision based on one of these two. Well, technically we're going to make a decision based on H sub O, but we have two options. H sub O is more believable than H sub A, or H sub A is more believable than H sub O. We get into things called reject and fail to reject, but that'll be later in this video. So you got to think that if this is the statement that is most believable, that it doesn't seem like it does take more than 3 minutes, then we're saying that it takes 3 minutes or less. I don't like this. I'll tell you I don't. In the literature, the null hypothesis is always assumed to be equal to. But guys, just keep in mind when you have what we call a directional test. Directional test, and well, I'll get into that in just a second, okay? What a directional test is, okay? So guys, keep that in mind. Now, let's set up some situations. All right, we want to test mu equal 3 minutes because we think it takes longer. What are you going to put in your answer on your assignment? H sub O, H sub A. I think it's easier to go down to H sub A first because H sub A is actually what you're trying to test. You think it takes longer? Mu, the opposite in the null hypothesis. What if the problem sets up takes less time? Well, again, H sub O, H sub A. Let's, I don't know if you saw that or not, but something popped up there. Thinks it takes less time. Well, let's go to the alternative. Put in what we're going to test. So mu greater than or equal to 3 in the null. The null will always be a conflicting, contradicting inequality to what we are testing. You will never have an equal to in the alternative. The equal to will only be in the null. Now the third option, we're just in an argumentative mood. And we'd simply like to test that the wait time is different. Now notice different is just kind of a generic, non-directional implication. So in this case, different doesn't mean higher or lower. It just means different than 3. And in that case, you would have mu equal to 3 in the null hypothesis. So guys, on Hawks, all of the hypotheses, null and alternative hypotheses that you are asked to set up will take one of these 3 forms. No reason to miss this problem. You've got it right here. I'll tell you exactly. Now, let's change things up just a little bit. Someone makes a claim. 52% of Ohioans support the Supreme Court decision to legalize same-sex marriage. All right, you look at that claim. It's an educated guess by someone, probably CNN, some media outlet. I've already been there. Trust me. Don't trust what these people tell you. It's just their claim. All right, it's based on what their sample says. But guys, there are good samples. There are bad samples. So keep that in mind. Okay, so maybe they got a hold of a good sample and that 52% is accurate. Maybe more than likely they got a hold of a bad sample or a not so accurate sample. So we want to test it. Now you've really got 4 options here. Option number 1, seems reasonable. Don't test it. 52%, I'm okay with that. I don't need to test it. Let's go have a beer together and chill out. Well, in that case, you don't even need a claim or a test of hypothesis. But let's say you want to test it because you think more than 52% of Ohioans support the Supreme Court decision. H sub O, H sub A. Now, guys, we're talking about a percentage here, right? So if we want higher, we would have greater than 0.52. The conflicting inequality would be that. Always the same number goes there. Third thing, we want to test it because we think that less than 52% of Ohioans support the Supreme Court decision. P less than 0.52, start down here, go up here and put the opposite inequality. The fourth option, we're just in an argumentative mood. And turns out this is the way we usually test hypothesis. We just want to test it. We think it's different. We don't think it's 52%. We think it may be 55. We think it may be 48. We don't want to come in and commit to a direction. We just think it's different than the 52% that some of these media outlets have said. All right. There you go. That's the way you set it up. Guys, same dynamics here. Same thing going on as with the mean, except when you test a percentage, you use P. When you test a mean or average, you use mu. Okay? Only thing going on. Only thing different. Part 2. I got to be consistent. How did I do that? I just did okay, anyway. Step 2 is you state alpha. Now, alpha turns out to be the probability of a type 1 error. We're going to get into that in a later video. Common choices of alpha. Or 0.001, 0.01, 0.05, 0.10. Alpha is technically the probability of a type 1 error. So if we set our alpha at 0.01, we have a 1% chance of committing a type 1, a 5% chance of committing a type 1, a 10% chance of committing a type 1, only a 1 in 1,000 chance of committing a type 1 there. There's something else that we'll learn about called beta, the probability of a type 2. As these go down, betas go up. So guys, we usually find a common ground. Alpha is almost always set at 0.05. Now, to get you to learn more about alpha, it won't necessarily be set at 0.05 in your assignments in Hawk. They will fluctuate this thing just to make you think a little bit more about how you set up critical values and calculate things called p-values and different things that I'll teach you later on. But typically alpha is set at 0.05. This is just, in my opinion, the value that sets the line in the sand. We make a claim of 3. How far away from 3 is acceptable to say that that difference is just because of sampling variation, but where does it go too far? We've got a certain range in there, sampling variability. We expect samples to vary. There's no reason to come out and get a sample mean and think we're going to get exactly 3. Samples are going to vary. We're going to get something not equal to 3, but maybe it's close enough to 3 to where it's not evidence against the claim of 3. How far away from 3 does our sample mean have to be to say, okay, dude, we need to step back here. We need to think, I got a sample mean of 4.5 minutes. If your claim is true, that seems kind of rare that I would get something of 4.5 minutes, again, assuming that your claim is true. And we might say, well, I don't think your claim is true, and I'm going to reject it. And if that happens, I'm going to teach you how to do what to do. So anyway, guys, step number 2, what do? You set your alpha. And your alpha is the line in the sand. Okay? Step number 3. Now, guys, this is where it gets wacky. There are 2 approaches that you're going to have to learn. The 2 approaches are either the critical value approach or the p-value approach. In the literature, the p-value approach is the approach that we take. So that's going to be the one that I'm going to teach you first. I'll come back and show you how the critical value approach. Now, guys, this is by far the most complicated part. I was a student long enough to know that students don't like 2 approaches. Students want 1 approach, and that's it. But I'm going to teach you what's called the p-value approach. The first step in step number 3 is to create what's called your test statistic. Your test statistic depends on the test that you are conducting. So the 3 confidence intervals that we have looked at so far unknown mu, sigma known. This was called a z-interval. If we want to estimate an unknown mu, sigma is not known, then we used a t-interval. And if we wanted to estimate an unknown p, a percentage, does anybody remember what we used? We used a 1 prop z interval. Now, guys, confidence intervals and test of hypothesis are very similar. Both of these fall under what we call inferential statistics. So changing from confidence intervals to hypothesis testing, we can use the same framework that we used in confidence intervals. Instead of an unknown mu, we want to test the claim about a population mean where the population standard deviation is known. We use a z-test. If we want to test a claim about a population mean, the population standard deviation is not known, then we're going to use a t-test. And if we want to test a claim about a percentage, we use a 1 prop z test. All right? Now, guys, I'm not going to teach you these. We're not going to learn these in this class. These things are rare. They're rare, and we don't have enough time we don't have enough time to waste any time. And these things are extremely rare in research. Those of you that are nurses, those of you that are in physical therapy, occupational therapy, all these different things where you're going to use statistics one day, trust me. You're never going to run into a z-test or a z-interval. It's just not going to happen. You're going to conduct t-test. There's a chance you're going to get into one prop z-test and chi-squares and different things down here. But these are the two most common, so these are the two that I am going to teach you. Guys, remember this one deals with the t-distribution. This one deals with the z-distribution. T, z. Okay? So we get into what's something called an underlying probability distribution, underlying sampling distribution. T-test used the t-distribution. Remember, they're a function of degrees of freedom. The z-test uses the z-distribution, means 0, standard deviation 1. We have talked about that ad nauseum. If you're sitting there thinking, what in the hell is he talking about? Then you haven't done your job up to this point. We've talked about that ad nauseum. All right, gang, let's talk about what a test statistic looks like. All test statistics. Well, I swear I can spell. I just can't see. All right, all test statistics have 3 parts. T or Z, depending on what we have. Three parts. Every T statistic, every Z statistic, every test statistic that we encounter in this class. Now, there are other test statistics we won't get into, like an F distribution. Forget I said that. The ones that we run into in this class will fall into these two, one of this form, 3 places. This will be the claim in H sub O. That'll always go there. This will be our sample mean or our sample proportion. And this will be our standard error. So for test of mu, sigma not known, what's the test statistic going to look like? T, because we use a t-test, which comes from the t-distribution, which uses the t-test statistic. We're going to take a sample mean. We're going to subtract it from the population mean that we made the claim about. And we're going to divide by the standard error. And you all should know by now that the standard error for these is Sx divided by the square root of n. What if we want to do a test of a percentage? Those use the z distribution. So you're going to have the z-test statistic. What goes into 3 parts? The sample, the claim, over the standard error. All right, so those are our test statistics. Now, gang, back to the Tim Hortons. Back to the Tim Hortons example. What do we want to test? And please don't go like complaining to Tim Hortons. Dr. Darbo said it took 3 minutes. I sat here for 6 minutes. I don't know how long it takes, okay? I'm just making kind of an educated claim based on, educated guess, based on my 100 or so times that I've been to Tim Hortons over my 21 years here at Shawnee State. I don't even think they've been open 21 years, but they've been a while. So, if I were carrying this out, just as an example, I really don't know how long it takes. I don't really have any reason to think it takes longer or any reason to think it takes less than. So I would probably just test that the mean is equal to 3, the mean is not equal to 3. Next thing I would do is I would set my alpha value at 0.05 because that's just the standard. That's the industry standard. I know that I'm testing mu. I don't know anything about the population standard deviation. So I know that I'm going to conduct a t-test, and I know that my test statistic is this thing right here. So I decide to stalk Tim Hortons from the time at 8 a.m. to 10 a.m. every day for the next 14 days. And let's say I take 3 samples per day, randomly selected, and I find a mean of 3.2 minutes. The claim, back up here, the claim in the null hypothesis always goes right there. This is what I got from stalking Tim Hortons. The standard deviation of my measurements was 0.8, and I stalked Tim Hortons and took 51 measurements. Okay? So guys, my sample consisted of n equal 51 measures. So I stalked 51 cars. I stalked them. I watched them pull up to Tim Hortons. I started the stopwatch. When they received their order and pulled off, I hit the stopwatch and I wrote down their time. I did this for 51 cars. I found that the average of those 51 cars was 3.2 minutes. I found that the standard deviation of the wait times for those 52 cars was 0.8 minutes. I want to use my sample information to test the claim that it takes 3 minutes to wait in Tim Hortons. So again, the first thing I'm going to do is I'm going to set up officially what I'm going to test. I'm going to set the line in the sand. I'm going to look at the criteria that I'm testing. I'm going to let Dr. Darbro teach me that a t-test is what I need to do that. So therefore, I have to set up a test statistic. The test statistic is the sample information minus what I'm testing divided by the standard error. We want to see how far in standard errors our sample is from what is being tested. Our test statistic is 3.2 minus 3 divided by 0.8 divided by the square root of 51. So my sample mean is my sample of 3.2, standard deviation 0.8, sample size of 51 is 1.7854. Okay? I'm going to go out to 4 places just because I can. These things are typically reported to 2 places, but I want to go out 4, okay? And I'd encourage you to do that. Well, I'd encourage you when you're asked to do a problem like this, go out however many places Hawks ask you to go out. All right? So this tells me that our sample mean is 1.7854 standard errors above. Why above? Because this is a positive. T-scores can be negative. If the mean had been below 3, we would have created a negative here. than we would have below there, okay? So our sample mean is 1.7854 standard errors above the claim that the mean is equal to 3 minutes. Now, this is the weird part. We next come in and we use our test statistic to create what's called the p-value. Now the p-value is just the area to the right, left, or between. This is where it gets hard, guys, and I'm going to give you the rules for calculating the p-value based on how you've set up your alternative hypothesis. Okay, to calculate the p-value, it's just the area under the curve and in this case, this is the t-distribution. Degrees of freedom equal 50. Remember, degrees of freedom is just n minus 1. So it's the area under the curve corresponding to our test statistic. Now, guys, again, this is where things get kind of funky, and this is something you need to write down. This needs to be in your notes. How to calculate a p-value. It would help if you could see that. It all depends on the alternative hypothesis. When it comes time to calculate a p-value, focus solely on the alternative hypothesis. And it depends on which one of these you have. If you have an alternative hypothesis that has less than the area that we are interested in is the area to the left of our test statistic. If we have an alternative hypothesis that's greater than, it's the area to the right of our test statistic that we're most interested in. If we have an alternative hypothesis that's not equal to, then it's the area to the right of our test statistic plus the area to the left of the test statistic that we are interested in. If we say something's greater than, then it's going to have to be way above our claim. Guys, what we assume in this is we assume that our claim is smack dab in the center of the distribution that we're drawing our samples from. How far away does this test statistic have to be before we say it's too far above to buy this claim? How far below does it have to be before we say it's too far below to believe the claim, based on we're testing below? And a not equal to, we say, well, we don't care whether it's above or below. If it's too far away in either direction, then we end up making the decision, okay? So what